Thank you so much for the kind invitation of Professor Takahashi, and I'm so glad to have a chance to report our research work here. It's the first time to visit Kyushu. I think I would be enjoy this business trip. I'm going to give a talk on the functional biomaterials for the understanding the processes of oxidative stress in the brain. I'm from I²CNER University. Our university is located at Shanghai. You will have a chance to visit China. Please visit our university. And you know the oxidative stress, we breathe the oxygen every day, and the reduction of the oxygen, for example, the superoxide anion, hydrogen oxide, and the hydroxyl radical, they all called reactive oxygen species. Actually, in normal condition, the ROS is not so high the concentration in our human body, just 10⁻⁸ to 10⁻⁷ more. However, upon anemia, infection, UV education, and so on, the concentration of the ROS increased very dramatically to the 10⁻⁴ to 10⁻³ more, resulting in a lot of diseases such as cancer, brain diseases. And you know, actually the neurodegenerative diseases, including the Alzheimer's disease, typically involve the higher levels of oxidative stress, the damage from ROS, and for example, the superoxide anion, hydroxyl radical, and the metal ions, the copper ion, and the iron ion. Now, more than 35 million people in the world are suffering from Alzheimer's diseases. However, the mechanism is still unclear at the present stage. The most proposal of the mechanism is shown here. For the oxidative of the copper from the copper 1+ to the copper 2 can trigger the reduction of the oxygen to the superoxide anion and hydrogen peroxide, or the hydroxyl radical. And the production of the ROS will give rise to pH decreasing, and brain acidosis will augment the oxidative stress. However, we always use these electrophysiological techniques to obtain the brain function and the brain disease, to evolution the mechanism of the brain diseases, and to know the neuron-to-neuron communications. For example, you know the very famous place cells. We know our position and the direction to go here to there. And this Professor Kiefer, he obtained the Nobel Prize in the physiology or the medicine in 2014. He found the place cells. They always use I just said, the electrophysiological techniques. However, how about the chemical signals? You know, the chemical molecules plays a very important role in the brain function and also the diseases. So electrochemical in vivo analysis methods, they provide the higher spatial and temporal resolution, more accurate reflection, and the easy establishment of the diseases models and the direct association with the etiology. So our group, we are interested in the development of new analytic methods for the understanding the oxidative stress processes by improving the accuracy, selectivity, and the sensitivity for fulfilling the requirements for detection in the brain. We have developed several analytical methods, for example, for the superoxide anion, pH, and copper ion recently. our strategy, we use this carbon nanotube 5. We fabricated this 5. And the diameter is about 10 micrometer, and implant this fiber into the brain in the different regions of the brain. For example, the stratum, hippocampus, and the cortex. And then use micro-sized this civil chloride as a reference electrode. And here is the same imaging of the carbon nanotube 5. You can see here we spring the carbon nanotube as a fiber, and here is the single fiber TEM imaging. And we also compared with the carbon 5 microelectrode and the conventional carbon 5 electrode. We found that about 170 millivoltage overpotential was reduced. Then we also calculated this activation energy. We found more oxygen-containing groups and oxide tips after acidification is favorable to the electron transfer, and resulting in the reducing of the active energy. And then we use this Prof, this 5, and for upon the ischemia, the oxygen will first be decreased very clearly. So we use this Prof, and heming is the center of lots of protein. For example, hemoglobin. We use this molecule, hemo, and conjugated with ferrocene. With very good electroactive molecules conjugated together, this molecule to form these molecules, and modified on the carbon nanotube 5. And this hemoglobin is very sensitive to the oxygen change. And we also found these molecules is also shifted the potential with the pH change. So we use this one probe to detect two signals by the current and the potential outputs. And here is the data you can see here with the increasing concentration of the oxygen, only the peak current increase very clearly, and with the increasing of the pH, decreasing of the pH, the potential shifted positively. And then we use this relationship imaging about the peak current and the peak change of peak potential change, and we can optimize these two signals. And we implanted this probe into the brain. For example, in the stratum, we found that the oxygen decreased very largely upon ischemia by 44 micromole. And the pH also changed very clearly in cortex about 0.34 and in stratum 0.47. And we also use this model for the investigation of the glucose and the pH, and we also found the glucose decreasing. Then we use another method to check the pH pricing. In the brain, the environment is very complicated, so we synthesize this compound. Here can capture the proton, and then the ferrocene, and the potential of the ferrocene may shift very clearly, and then we use this molecule to detect the pH in the brain. And here we, for amplify the signals, we electrodeposited the gold nanoliths on the carbon nanotube, carbon 5, and you can see here like gold leaves. And here is the this is the responses for the pH, and this we also modified a very stable molecule. For example, ferrocene it is placed as a inner reference element. So we can use the potential change between these two peaks for quantification of the pH here. Only this peak shifted with the pH, and here you can see it's very stable upon the pH change, and you can see the slope is about 58 millivoltage per pH. It is a Nester processes. And we also checked the selectivity of this probe against the other metal ion, for example, the sodium, potassium, and the calcium, and the other, also the ROS and the amino acids and the neurotransmitters, which may co-existing in the brain. We found almost no response for the other biomolecules. Then in the brain, we found in the striatum, hippocampus, and the cortex, and they change very clearly. In the initial, the pH is about 7.2 or 7.13. Not we imagine just like 7.4. And it will decrease very clearly in the striatum. Down to the 9.75 in hippocampus, only 6.5. And we also checked the pH change upon the different time. We found that only within 5 minutes, the change is very clearly, and almost no change was observed after that. Then we want to know how about the generation of the superoxide anion. Actually, we have done this work for a long time. We optimize a lot of proteins to recognize the superoxide anion. Here we use the superoxide dismutase. You know, it is a very specific protein for the superoxide. So we use this oxidative and reductive processes for the determination, electrochemical determination of the superoxide anion. And we modify this NTA. These molecules can immobilize the STOD very stably by the covalent bond between the NTA and the histone of the SOD. Then we found that the electrochemical reduction processes was very successful, realized at this more electrodes, and the formal potential of this SOD was found about 20 millivoltage. It is between the formal potential of the oxygen superoxide and oxygen hydrogen peroxide, and the electron transfer rate constant is also very high. Then we use both oxidative and reductive processes to determine the superoxide anion. And in the brain, we found upon ischemia, the burst of the superoxide anion was observed, and for the reperfusion, unexpected, the superoxide also was produced very significantly. And you know, here the copper plays a very important role. So we want to know how about the copper in the brain for the change. Unfortunately, there is still no reports on this concentration of the copper in the brain. We use this superoxide anion. You know, the center, the metal center of the superoxide anion is the copper and the zinc. Also, we have another type of SODs, for example, the iron or the nickel. Now we use the copper zinc SOD as a as a target, and then we took the copper in advance and obtained the copper-free SOD. We named this as Apple SOD. We use this as a recognition element for recognize the copper. And meanwhile, we use the ferrocene hydroxyl modify these molecules as a reference electrode to improve the accuracy for determination in the brain. And here, gold microcage full of nanogrids were seized for improving the sensitivity. And then we use this electrode to determine the copper in the brain. Here is the imaging of the gold microcage. You can see here the diameter distribution of 1 to 1.5 micrometer with a big hole interest. And the wall of the cage is composed of nanogrids with a thickness of about 100 nanometer. And we also found the gold indicates a polystyrene gold here. And then we modify this gold cage on the electrode and further for the Apple SOD. And then we found only in the Apple SOD, a functional electrode can respond to the copper very quickly, and the other electrode had no response in these potential windows. And within the increasing concentration of the copper, this peak increased very clearly, and this peak for the ferrocene almost stayed constant. And we can use this the ratio of these two peaks to quantify the concentration of the copper from 10 nanometer to the 35 micrometer with a very low detection limit down to the 3 nanomole. The sensitivity is very high. Then we found the other metal ions and amino acids and the neurotransmitters had almost no interface toward the determination of the copper. And in the brain, we because of the two working electrodes, we implanted these two electrodes in the left and the right stratum, and another 2 millimole plastic panel was located about 5 millimole far from the one of the working electrode. Then the reference and the counter electrode will be introduced in this plastic cannula. And then we found for the black curves, you can see this is for the normal red brains. And upon ischemia, we found the concentration of the copper increased from 2.09 to the 9.3. And then we compared the concentration of the copper in the brain by our method. Compared with the results obtained from the I²CNER. You know, for this method, we cannot detect the copper concentration directly in the brain. We just use a pump to obtain the microdiacetate from the brain. Then we compared these two results. We found show a very good agreement. And after our publication of this work, lots of scientists asked me why the concentration of the copper-2+ increased so significantly, about 4.5-fold. I think there may two reasons. One is that upon ischemia, just demonstrated in our previous work, you know, the pH decreased very clearly. So maybe the protein containing copper, the copper containing pure protein, when the pH decreased, this kind of the protein may release the free copper from this protein structure. Another reason may be the oxidation of the copper 1+, the copper 1+ was oxidized to the copper 2+ upon the ischemia. So we want to know how about the change of the COP2+ in this situation. Here we see this compound for specific recognition of the COP1+, and we also change the length of this alkyl chain and the kind of the food. And we optimized and we found this kind of the molecules was optimized as a very effective prop for the recognition of the COP1+, and then this ABTs, these molecules were used as the inner reference electrode, and we found here this peak for the is the AQ, which is very sensitive to the pH, and no peak was observed here, just the peak for the AQ and the ABTs. And with the addition of the COP1+, you can see here, this peak appears, and after addition of the EDTA and disappeared this peak we can observe. And this means this peak was ascribed to the COP1+. And with the increasing concentration of the COP1+, this peak increased clearly. And we use this inner reference and the ratio of these two peaks to obtain linear range for the copper from 0.5 to the 9.5 micrometer. And this peak we can obtain the potential change to know the change of the pH. So we can simultaneously detect of the COP1+ and the pH with potential current double syndrome outputs. And we can found that especially the COP2+ and the other zinc nickel metal ions had no interference for the detection. We also checked the copper-containing protein. We found no response for this protein. That means the concentration of the COP1+ determined by our method is just a free copper. Then in the red brain, we found, for example, in the stratum, the COP1+ just increased by 1-fold, and in cortex only 0.5-fold in the cortex. And that means that is not so higher than the change of the COP2+. This maybe some of the COP1+ was oxidized to the COP2+ upon the ischemia. Okay, you know, upon ischemia for the 1 hour or more 1.5 hour, the neuron death was occurred after ischemia for only 1 or 2 hours. How about the signaling pathway in the living cells? We now want to know because the concentration reported in our previous work, just the intracellular concentration of these molecules. We want to know how about in the living cells. So according to the linear ratio, maybe the calcium overloading is a very main reason. So recently we developed a mitochondrial targeted DNA nanoprobe for the real-time imaging and the simultaneous quantification of the calcium and the pH in neurons. Here we designed this nanoprobe here. We see this compound as a selective recognition of the calcium, these molecules, and conjugated onto the carbon nanodots. And the fluorescent carbon nanodots is not so big, just 1 to 2 nanometers. And meanwhile, we use this conventional pH probe, FITC here. Then we use the DNA nanostructure to capture these 2 molecules, and then we use AFC 660 as an inner reference electrode. And for the targeting of the mitochondria, we use the TPP, this TPP for the targeting mitochondria. You know, mitochondria is an energy factory in the living cell. The concentration change is very high in these sub-organs, and so we use this for the targeting mitochondria. And here is the data for our probe. You can see here for the calcium increasing, this peak increasing very clearly, and this for the pH change. Then we can obtain the calcium sensing from 1 to 390 micrometer, and with a detection limit of 300 more, and the pH change from 8 to the about 5.5. You know, for the mitochondria, the pH is around 7.5 to the 8. So this probe can detect the pH change in the mitochondria very suitable. And the simultaneous sensing also can observe here. Both change the pH and the calcium can obtain two linear ranges, and this should our probe can be used for the calcium and the pH sensing at the same time. And we also checked the reversibility of the pH probe, and we found the rate constant is very high, just several hundred milliseconds, and they have no crosstalk for the determination of the pH and the calcium. And for the selectivity and anti-interference, we found our probe also show very good performance. And for the further imaging and biosensing in the neurons and the cells, the cytotoxicity and the biocompatibility of our developed probe also checked. We used the MTT, this method. We found the cell viability still maintained higher than 90% after incubation of our probe for the 48 hours. In neuron and in health cell, we also checked this. And we also used flow cytometry to examine the biocompatibility. We found also almost no obvious change were found for the compared with that control experimental. And we used this method to check the immobilization of the biomolecules on the DNA nanostructure, and then for the biosensing imaging, we found we first found the co-localization. We carried out these experiments. We used the conventional dial for the imaging of the mitochondria. Then we converted by the cell with our probe. We found the person correlation efficient is about 0.96 or this 0.95. So this means the developed nanoprobe can enter into the cell and almost located in the mitochondria. And then we checked calcium sensing imaging, and mitochondria. We added the calcium outside the cell, and then we found the calcium also increased very clearly in the mitochondria. And then the pH also increased with the increasing concentration of the calcium. And also we changed the pH of the cell, and with the pH decreasing of the mitochondria, and the calcium concentration increased very clearly. And upon the, we also want to know why this pH can induce the change of the mitochondria. You know, this ASICIC1A is a pH-sensitive channel in the member of the living cell. Also, the scientists found that this channel also now in the member of the mitochondria. So we also use the inhibition of this channel. We call the PCTX1. We found with the addition of this inhibitor, the no observation of the calcium increasing was observed. This means this channel plays a very important role for the pH-induced overload of the calcium. And then we checked the effects of the superoxide anion, the effects of this ROS on the neuron viability. And we found that the neuron viability of waste decreased very clearly with the increasing superoxide anion concentration and the stimulation time. And this channel gene, we deleted this gene from the cell, and we found this channel can protect the neurons against the superoxide anion-induced cell death. And we also real-time. We also carry out the real-time experiments, and we found after stimulation with the superoxide anion, the cytoplasm pH decreased very clearly, and then the cytoplasmic calcium concentration also increased. Further, then the increasing in the mitochondrial calcium concentration was observed, and an increasing in the pH. So this is just our observation of the real-time experiments, and this pH-sensitive channel also very important role in this. First, the extracellular superoxide anion entered the cytomer to induce the acidification and the calcium burst. Then, this pH-sensitive channel activation on the mitochondrial member regulates the calcium and the pH in the mitochondria. Then, the mitochondrial calcium overload and the alkalization was found to be caused. So the neuron viability of waste decreased with the increasing A-beta concentration. We use the A-beta to induce the ischemia for this neuron, and we also found this channel protects the neuron from the A-beta-induced neuron death. And we investigated the signaling pathway of the A-beta-induced neuron death. Here, just the preliminary data. Okay, then we summarize here. Over the past more than 10 years, we just have success in the measurements of the molecules in the brain and in the living cells. For example, the ROS and the pH, temperature, oxygen, and the related metal ions, copper, calcium. They are always finished in our work. We are published in the near future, and the neurotransmitters and the amino acids. And then we use our developed Prof. We found the oxygen upon the ischemia, the oxygen decreased very clearly, and the pH also decreased by 0.5. And the superoxide gave the burst, and the copper and the potassium increased very clearly, and the calcium decreased. And the superoxide anion transferred from the membrane into the living cell, and the pH increase here, and the calcium increased by more than 100-fold, and the potassium decreased very clearly. This is just a preliminary evaluation in our laboratory. And finally, I would thank the foundation from the Nature Science Foundation of China, and also the hard work of our students, and the cooperation with the other cooperations from Fudan University and Tongji University and hospitals. Thank you so much for your kind attention. Thank you very much.